All right, so welcome back. Today is the last lecture, of course, before your midterm, which is a week from today, right when you come back from the break. So do keep that in mind. We'll announce, of course, full details later this week with our retrospective. But today what we're going to do is we're going to review and look at some of the tools, and I'm going to introduce you to a brand new tool that we've previewed before. But some of these tools, the debugging and these tools that we're going to talk about, you've had exposure to them or you've had some working knowledge with them. For example, Git. You've been cloning stuff for hacks and labs the entire semester at this point. And in your first hack, we had you actually commit something to Git and work collaboratively with somebody else, right? That is a fundamental tool to software development. It's a distributed VCS, version control system, that allows you to, manage code in the cloud, whatever, right? So that other people can work on it, contribute to it, and contribute to not a centralized repository, but a distributed repository. So that's one tool that you should get into the habit of using going forward if you haven't already. Of course, you're using it ever on a weekly basis, but using it for your own code, that's what you should be doing, right? You've also had some exposure to build systems at this point. The build system du jour for C is going to be make, or its predecessor now is called CMake, and it's a little bit more powerful version of make, but we haven't used that in this course. Of course, you can also have other tools for dependency management. Now, we've taken care of most of that for you. For example, you might have a dependency on an image library, right? In which case you would have to you'd have to build a tool that could go out and get that library that you depend on, update and maintain that library that you depend on. But we've taken care of that for you by getting those libraries and putting them into the repos as needed, right? But there are tools to do that, to manage dependencies and stuff like that. You also have package management and a whole bunch of other tools that go into basically building an application. In fact, building an application is a job unto itself if it's a complicated or complex enough system. It's called DevOps, or development operations. You could have somebody whose entire job it is to maintain these build scripts and automated testing and all that stuff. And they don't even write a single line of code. They're just responsible for making sure that all the code actually compiles. And that's an entire job unto itself if it's complex enough. You've also had exposure to unit testing in an ad hoc manner, in an informal manner, and finally in a formal manner using the CMaka library for that. Testing, right? You're not always going to have a web grader that you can throw something at and see what percentage of test case do I pass, right? You have to design your own tests. Not only that, but the web grader is a black box tester. You can't look inside and see what's going on. It only tells you that it passes everything or that it fails something, right? And sometimes it doesn't even do that because you've got a segmentation fault and it just errors out entirely. So you need to get into the habit of testing. And that's what we'll demonstrate that here in a moment when we do our midterm review. But anyway, you've also had some exposure to static analysis tools. The most basic one that you can have that you've had access to is simply just GCC. Turning on all the flags, on all the warning flags, the wall flag, remember that? That will basically, it'll go through and statically analyze your code and look for potential issues called lint, right? And it looks at your code for potential problems before it compiles. There's another flag that you might be interested in, the W extra. It goes in, I don't think that it's any much different with GCC, maybe it's with Clang, I'm not sure. But it'll also go one level deeper with extra checks and extra warnings and stuff like that. So let me just go ahead and check and see what it does here. So I'm going to turn on the wall flag and the extra flag. What is it? Yep, extra. For this buggy program that we're going to fix here. Right? And it looks like it's almost exactly the same as the wall flag for that one. Let's look at another one, bounds here. There we go. All right. Looks like it's the same warnings as the other one, but you might be able to, depending on your program, you might come up with some more warnings if you use the W extra flag. There's another compiler called Clang, or C-Lang, for C language, and you can use that as a static analysis tool as well. It's a compiler, so if you wanted to, you could go ahead and use that instead of GCC. But here, I'll go ahead and compile my bounds program here. We'll take a look at what that is in a second. And it compiles just fine with no warnings. But if I want Clang to tell me if there might be something wrong potentially with this program, then I can basically turn on all the warnings for Clang as well with bounds, with hyphen analyze. There we go. Unfortunately, nothing came up with that. So let's go ahead and look at the other one, array. .c. There. So other warning, now your mileage may vary. Clang and GCC are just two different compilers, and they might have different warnings, right? If you don't get any warnings with another one, then try the other one and see if you get different warnings, vice versa. Anyway, that's Clang. That's yet another compiler. There's also a tool called Infer that would allow you to, it's a Facebook tool, that allows you to compile your program, and Infer, I believe, will watch while it compiles, looking for potential issues, and then you can go ahead and analyze it afterwards. I'm not going to demonstrate that because I don't have an example that it would work on, but you can go ahead and, well, I guess I can. Let's go ahead and try it with that array utils, or array.c. There we go. So it just captured all the information as I compiled that program. Now I want to, what was it called? Infer analyze. All right, there we go. So it simulates the program, and then it comes up with several potential issues. Now these are not absolute bugs, right? But it comes up with several issues. For example, let's see. This int type is never used, right? So that's a clear red flag right there. Why do I have a variable that I'm not using? I wanted that variable, and I wanted to use it, that's why I created the variable, but if I don't use it, that's a huge red flag that there might be something wrong with it. That I intended to use it, and that's the bug. I'm not actually using it. You do have a memory leak here. We called malloc on line 45, but it's not reachable after line 50, right? So it tells you exactly where you allocated it and where you lost your reference to it. Same thing here, that we've got a potential null dereferencing issue. Whatever it is on line 45 that we created, it could be null, and we might have dereferenced it here on this line by trying to access the ith element. So it's not an absolute assurance that that's a bug, but it's a potential issue that you might want to take a look at a little bit closer. Right? And it also tells you, the line numbers to take a look at. Uninitialized value, right? The value read from sum was never initialized. That's a huge red flag right there. Okay. All right. So that's static analysis tools. Dynamic analysis tools are like Valgrind that we've already briefly demonstrated before. That if I go ahead and compile something with the GFLAG, we'll go ahead and do it with the array.c here. I'm going to shut off the warnings so that you don't know what the bugs are. There, I shut off all the warnings by just going with lowercase w. I'm going to run this through Valgrind. Actually, before we do that, let's take a look at what this program is actually doing. So I've got this function that generates a random array. I've got this function that takes an array and its size and then tries to compute its average. And then I've also got this function that takes an array and simply prints it to the standard output. I'm going to define a default value of 10 right here. And so let's walk through this and see what happens here. So I'm expecting a command line argument, right? And if I don't receive a command line argument, then we exit and quit. Otherwise, I'm going to go ahead and create a random array of size n, where n is what has been given to me as a command line argument. Oops, sorry. Let me go ahead and move this over. So, there we go. All right, so everybody can see it. Anyway, I'm going to create a random array here, and I'm going to print out computing the average of this. I print it out so that you can see it. And then I call this average method, this function right here, and then I report it. Okay. So you can kind of see what these, you can kind of expect what these would do. Random array, that was in your lab a couple of weeks ago. Average just goes through, adds them all up, and then divides by how many there are. Print array just simply prints them all to the standard output. So from first glance, it all looks pretty straightforward and correct, right? Let me go ahead and run it though, and of course I get a segmentation fault. Valgrind will at least tell me what line number the segmentation fault happened on. Valgrind, a.out, 10. Right. There we go. So there's at least one error here, and because of course it resulted in a segmentation fault. And if you read this for all it's worth, it tells you exactly where. Right? On line 67. It was an invalid read of size 4. Remember that was an integer array? And so if I'm trying to print out one integer, how many bytes is that? 4. So clearly I am making some sort of error here on line 67. In fact, it's not stacked, malloc, or recently freed. Right? And, there's no initialized memory here is basically what it's telling me. So there's something wrong on that line. Let me look at another program here, Emacs bounds. Right. So this one is even simpler. What am I doing on these few lines? I'm creating an array of integers of size 100. Then I'm iterating it over it and setting it equal to 1, 2, 3, 4, 5, 6, 7, all the way up to 100. Do you see an immediate problem though? Nobody? Okay, good. Then we'll allow Valgrind to tell us what the problem is. What about this one? I'm going to create a string of size 5. You see the 5 right here. And then I'm going to expect it to hold my name, CHRIS. And then I print it. Do we see a problem there? Maybe. Let's find out. So I'm going to go ahead and compile it. Always remember the GFLAG, bounds.c. If I run it, it looks like it runs perfectly fine. It prints out my name and we're done. Right? But if I run it through Valgrind, then it comes up with actually 4 different errors. There were 4 errors. They didn't manifest with a segmentation fault. It didn't manifest with an abort sequence or anything like that. But Valgrind was able to detect that I was doing something wrong. Right? There's an invalid write of size 4 on line 10. Right? Let's go ahead and go back into that and see what was on line 10. There's line 10. Can you see what's wrong? Does that look right to you? Does that look like an idiomatic for loop for iterating over an array? Probably not. What did I do? I went 1 extra trying to write 4 bytes that didn't exist. Okay. Now it didn't tell me that it happened at index 101, right? Or it didn't tell me it happened at index 100. But it was able to detect that I went out of the bounds of this array. Let's take a look at the other error message here. There's an invalid write of size 2 on line 14, and then an invalid write of size, or read of size 1 on line, when I tried to print it, right, on line 15. So again, let's go ahead and go back in there. Lines 14 and 15 are suspect. So lines 14, what am I doing? Can you fit CHRIS into an array of size 5 with a string? Nope. What do you need? A validly null terminated character. So when strcpy tried to copy in CHRIS and the null terminating character, that was the invalid write. There was 1 or 2 bytes in there or something like that, right? And then the invalid read was when I actually printed it out, because CHRIS and then it went on or something and printed the null terminating character that was not part of the array. Valgrind can help you detect these kind of things, because if you just run it blind, it looks like it runs perfectly fine. Okay. All right. Oops, let's go back over here. There's also performance testing or perf testing. You can actually profile your code. We'll look at this later on. A tool called gprof, which is GNU's profiler. Okay. What I wanted to do is I wanted to focus on another tool called a debugger, a live interactive program that allows you to run your program line by line without it immediately quitting, right? So for example, if I just run the program, programs are run immediately, right? Especially if they're small programs, they're ephemeral. They go quick, and there's no way to see what happens. What I want to do is I want to run my program up to a certain point, and I want to take a look around. Like, what are the variable values? And what happens when I go to the next line, and then the next line, and then the next line, right? I want to simulate the program so that I can see what's going on, so that I can probably detect the bugs. So I hope to detect the bugs. A lot of people try to use printf, right? What are the variable values up to this point? Print them out, print them out, print them out. That's a poor man's debugger. It's a poor man's debugging because, first of all, it means that you have to put in a bunch of print statements, and then once you fix that bug, you have to go back and delete all those statements. Oh, now there's a new bug. All right, go back and restore all those printf statements, right? And not only that, but it's not a proper way of debugging because it's not predictable. The standard output, if you're printing to the standard output is actually a buffer. And what could happen is that you could be printing a bunch of stuff to the screen, and it hasn't actually manifested itself to the screen yet, but it's sitting somewhere in a buffer that's going to be written to the screen at some point in the future. Your program dies because of a segmentation fault or whatever before this stuff gets a chance to be printed to the screen, and you never see it. So when you think, oh, the bug must be here because that was the last print statement I saw, no, the bug was actually down here because all those print statements in between, they're just stuck in the buffer. They just never got printed. You'll never be able to predict that. It's unpredictable. So what we're going to use is a debugger called GDB, and it stands for GNU's Debugger. GDB, DB is debugger. Right? There's a full list of commands that you can use here, along with some other helpful tools. But basically, a debugger is a program that simulates and runs another program and allows you to pause the execution, view all the variables, like take a look around what's going on, step through a program. So I want to go to the next line, the next line, the next line. That line calls a function. Okay, jump to that function and start going to that function line by line by line to see what's going on. You can set breakpoints to say that, okay, well, it all looks good up to here. I want to jump to 1,000 lines below. You don't have to go next, 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 and run through 1,000 lines. You could just say, all right, run the program from the current location all the way down to line number 5,000, right? And then pause so that I can take a look around. You can set breakpoints at functions, at particular line numbers, or you can even set what are called conditional breakpoints. If something's going wrong with a certain value in a loop, you can simulate that loop up until it reaches that value, then it will pause for you, and then you can take a look around and see what the variable values are. Okay? GDB is a TUI debugger, that's Text User Interface Debugger. You'll work with it from the command line, okay? And I'm going to demonstrate that in a second here. But to do so, you need to use that GFLAG. The GFLAG is just for GNU's debugger, but basically it retains all of the line numbers, it retains all of the function names, and all of the variable names. All that stuff is lost when it gets compiled, because a compiled program doesn't care that you named your variable myAwesome variable. It's just a memory address to a computer. So if you don't compile with that GFLAG, you don't get these nice things like, oh, it happened on bounds.c line 15. Okay? To run GDB, once you've compiled, you just go use GDB a.out. So let's do that over here. This buggy. What was it? Arrays. So gcc g arrays.c. Remember, pay no attention to those warnings, right? Those are things that we're going to fix. And if I run this and I want to generate a random array of 10 elements and compute its average segmentation fault, there's a problem. I need to go into a debug mode here. So GDB a.out. Right? Now that opens up the GDB interface. It's a text user interface. So you're not going to have these point and click icons and buttons and everything like that. It's all at the command line. All right, so it's prompting me to do my thing. It's just waiting for me to interact with it now. I want to run my program. So run, run. And it ran, and you see that it exited with some code, right? That they're starting this program, usage, blah, blah, blah. Process exited with some error code 01. Right? Something happened, right? But it went right by really quickly, right? So what I want to do is, in fact, there's no error message at all. Okay, so let's quit out of this and let me. Oh, by the way, to quit out of GDB, quit. Right. So let's go ahead and go back into arrays.c here, and we'll require this. If it's not equal to 2, then it exits with that. So did it not print that usage? Huh. Run. There it is. Usage. All right. We didn't provide a command line argument. Now, when you run from the command line, of course, you can provide command line arguments directly. I need to provide a command line argument here non-interactively. So let's go ahead and set args to be, how big of an array do we want to make? 10? Okay. So the arguments have been set. Now, when I run it, you see that I get that same segmentation fault. What line did it occur at? At line 67. There's some problem either at line 67 or prior to that. So what I'm going to do is I'm going to set a breakpoint and take a look around, right? Set a breakpoint at line 66, one right before it, because I know that it's going to fail on line 66. And let's go ahead and, not set, but break 66. There we go. Break is setting a breakpoint at line 66 in this file. Right? Now let's go ahead and run. Yeah, you can start it. You can start it over. It's only showing me one line of code right now, which is not too helpful. So what I'm going to do is I'm going to tell the GDB that I want to look at the entire code. Layout next. Does that look like our code? No. What does it look like? Does anybody know what that looks like? It's a bunch of assembly code. Remember way back when, way back in the first week, I showed you that compilation process, that it takes C code, compiles it to assembly code. That assembly code then gets assembled into machine code. This is the assembly code. We didn't write this. If you can debug from the assembly, but I don't want that. I want to debug from the original code. So I'll go ahead and go with layout src. src short for source. And it shows me all my code here. These are the original line numbers, and you see this B right here, which is a breakpoint. And the program is paused at this point, at this breakpoint. Right? So let's go ahead and take a look around. We can, what value of I do we have? Print I. 32,767. Does that sound right to you? That's already fishy, right? Why is it 32,767? Why? We never initialized it. Right? I've got a regular old for loop here, and I haven't gone to the actual first iteration of this. If I go next, let's go one more line, then we see that I is now changed. If I print I, you can see that now I'm on the first iteration of the while loop, or the for loop, excuse me. Now I is 0. Right? And I'm about to hit that segmentation fault. If I go next one more time, there, seg fault. Right? So let's rerun that again, right? And so all the way from the beginning, right? And sometimes it'll screw up and not print everything correctly. That's okay. Just go ahead and refresh the screen, right? And it'll refresh the entire screen, and now it's printing nicely. Okay. So I know that something's going to happen on that first iteration of that while loop. Let's take a look at the inputs. Let's go ahead and print n. Right. Remember that we set this up to create a random array of size 10. That looks cool. That looks good. But if I print a, that's just a memory address. Right? What's in there? If I dereference it, then I should get the first element of that array, right? You can't access that memory. I wonder why. So something must have happened before we even got to this print function. I need to investigate before this even happened. So what I'm going to do is I'm going to set another breakpoint. Sorry, not print, but break. Let's go ahead and break right at the beginning of the program. The beginning of every program is where? The main function. So you can break at a particular line like I did before. Break 66. That's a line number. It'll break on that line number. Or you can break at the beginning of a function, main. Or break at the beginning of this function, print array. Right? There. We added another breakpoint here. It's not going to appear at line 63 because this is the actual first executable piece of code. Okay, so let's go ahead and break at main as well, and then let's start the program over again. So run yes from the beginning. Okay, and refresh so that we can take a nice look at it. All right, now we can start walking through this line by line by line. All right, so n initially receives a value of 10, I believe. We can print it out and find out. Right? Yep, it has 10. The number of command line arguments, how many is that? argc. We've got 2 command line arguments. So we're going to go, now I predict that we're going to go into this if statement. And we do, or that we're going to skip the if statement, sorry. And we do. I'm going to go ahead and seed the random number generator, et cetera, et cetera. We read in that first command line argument. Was it successful? Print n, yes it was. Okay. So now I'm about to create this random array, right? If I just hit next, it's going to go over that line, right? Then go to the next line. That's not what I wanted. I want to investigate that function because that function might be buggy. So what I wanted to do is step into that function. So let's start over again from the beginning. Refresh. Next, 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 next. Now, instead of going to the next line, I want to go into that function. Step into that function. There we go. And now I'm at that function, and here's the first line. Again, let's make sure that everything is correct. In fact, it tells me right here that we've called random array on an input with 10. Okay? So next. Okay? I called malloc. You don't want to step into malloc or any standard library function, by the way, because that code probably is not even available. You could take a look at the machine code and the assembly code if you really want to, but it's probably not going to work. And probably the bug is probably not in malloc, right? If there was a bug in malloc, a whole hell of a lot else would be wrong, right? So, but I can take a look at what it gave me. Print a. Right? That looks like a valid memory location, does it not? It's some random memory location, but whatever. All right, so next, next, next. All it's doing is generating random numbers and then adding them to this array. I want to print that array. So print a sub 0. What random number did it get for the first one? 1. Print a sub 1. It got a random number of 0. Right? Print actually, no, it hasn't been set yet. So next, now print a sub 1. There, it got a random number of 4. Right? If you don't want to do this manually, what you can do is you can take a look at the entire array. Print a. I need to dereference it, I think, and then I need to tell it how many elements are in the array. So this is dereferencing a, and I expect 10 elements in there. When I do that, it'll print all of them. 1, 4, and then the rest are zeroed out because that's the default, apparently. All right? If I keep going, next, next, and then print that again, print, dereferencing a, and there are 10 elements in there, then I see that, okay, the next one was set to 3. All right, keep going, keep going. I want to go all the way to the end. So let's set a conditional breakpoint. Instead of me having to go next, 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 next 7 more times, I can either set a breakpoint at line 50, or I can set an addition, break at line 50, or I can go ahead and set a conditional breakpoint. Go all the way to the end of the loop when I is equal to 9. So break at line 48 if I is equal to 9. Okay? Now, I want the program to continue. I don't want to have to keep going next, 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 next. So I will say continue. Right? And by the way, how was I going next? I didn't type next every single time. It's so common that you just type n, enter, n, enter, n, enter. So I want the program to continue until this condition holds. I'm at the end of the loop. Right, there we go. Let's go ahead and make sure. Print I. You see that I is now 9. It skipped ahead 7 iterations. Now let's go ahead and print that array at 10. There we go. So everything looks fine with the array, right? Those zeros are still zeros, but that's because it randomly generated those zeros. So let's go ahead and go next, next, and now we've broken out of that while loop. Before we return, let's go ahead and make sure that what the array contents are. So print a at 10. All right. So 1, 4, 3, blah, blah, blah. Just remember that it's 1, 4, 3. Next. Next. And we've returned from the function. Okay. By the way, you can go up and down here to take a look at the rest of your code. Up and down arrow keys. Let's make sure that we received the array correctly. Now in this context, the array is called ARR. So let's go ahead and print ARR. Right? That's just a memory address. Let's go ahead and dereference ARR to get the first element. Can't access that memory. Okay, you can't even, if I can't access that memory, then certainly I can't print out the entire array. Right? What happened? I never returned it. Oh, okay. Bug number 1 found. So let's go ahead and quit. That, by the way, that'll clear all your breakpoints as well. So next time you run it, you'll have to reset them if you want to. And let's go ahead and fix that issue. Okay. So come down here to random array. What should I have done instead? I need to actually return the array after creating it. Okay. Recompile. Using the GFLAG, you can run it really quick to find out if it works, right? Does that look like an average of 10 numbers, all between 0 and 9? Probably not. So again, let's go ahead and fire up GDB, a.out. Set my arguments, set args 10, layout src so that I can actually see what's going on, right? It takes a little bit to load. I don't want to just run it all the way through it. Remember that it was all okay up until line 37. So let's go ahead and break at line 37 and run up to that point. There we go. Refresh it. Now I'm about to print this array. We can go ahead and go over this line, or we can go into the function. I'm going to go ahead and go over this line first of all. And, oh, I guess it didn't end up printing anything. So might there be something wrong? I don't know. Let's run it from the start again, and let's go ahead and break at print array. Right, and refresh. There we go. So continue. Again, you can just go C. Right. Next. I don't know why it's not actually printing here, but whatever. Right. Next. All right. I don't see any problems there, so next. There might be a problem in average. So I want to jump into that function to find out what's going on in there. How do I go into that function again? If I did next, would that work? No, I want to go into the function. I want to step into the function. So step or just S. There we go. Let's make sure that we've received everything correctly. Well, first of all, that looks like a valid memory location. It's of size 10. Let's print it out and see what's in there. So print a at 10. So 6, 7, 8, 1, ... You can pull out your calculator, add all those up, and see what the average should be. What should it be? 15, 22, 31. I shouldn't have done 10. All right, well, it's going to be something average. It's going to be close to 5, right? All right, so let's go ahead and look at the operation for several iterations here. Now note here that I'm just summing them up. Sum up, add the first one, the second one, the third one. Let's print what sum we have so far. So does that look right? No. What's going on here? Next. Print sum. Is it fixed now? Nope, it's different, right? It's some negative value ending in 35. And now it's some negative value ending in 27. So it is changing. Right? What I want to do is I want to set. I want to use this as an opportunity to set what's called a watch variable. I want to watch sum. In other words, instead of printing out sum on each iteration, I want to go ahead and watch it, and any change, it'll inform me about that. Watch the sum. Next. The sum has changed. Right? The old value was here. And here's the new value, right? What was in that array again? At 10. We added 1. So the addition seems to be working. Right. Next. Now, we're about to add 9. right? If I printed out I, we're on the fifth element, 0, 1, 2, 3, 4, 5, sorry, 4 right here. We're about to add 9 to it. So if I go next, what would you expect the value to be? Here's the old value. If I add 9 to that, then it's going to be like something ending in 17. There we go. But it's still negative, right? We started off wrong. What's going on here? Yeah. I never initialized sum. Let's rerun this from the top. All right. Run, yes. Refresh it. All right. So print array, next. No, I quit. Sorry. Let's just go ahead and fix it. All right. Emacs array.c. And let's come down here. What should I have done differently? I should have initialized it to what? 0. Okay. Got that fixed. All right. GCC. A.out. A.out 10. There we go. Still looks wrong, right? 3907 ... The average, that doesn't look right. So, once again, GDB. Let's go ahead and take another look at that average function. So let's go ahead and set our args to 10 and break at average. Right. And then layout source. So run. Now we're here. Now remember that the sum is now initialized to 0. Let's go ahead and make sure that that's correct. Print sum. Okay. I'm going to watch sum as it changes. And I'm also going to print out the array here. 7, 7, 6, 8, 8, 8, or 8, 0, 1, ... etc. Let's watch as it starts adding up that number. Next. Next. The sum went from 0 to 7 because we added that first number. It went from 7 to 14 because we added up that second number, which was also 7. What was the rest of it, by the way? Print a at 10. All right, 6, 8, 8, ... Next, 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 next. Print, let's also print I. All right, next, 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 next. Where am I now? 7, next, next. Print I. In fact, let's just watch I. All right, so next. I is now, or the old value was 8. Now we're at 9. Okay, remember that there is an array of size 10. Okay, and next. We sum up that last value, and we should be done, right? Okay. Next. Now the new value of I is 10. Next. Is there a sum value of 10, or is there an array value of 10? Print a sub 10. Yes, there is. It's 1041. Right. Did you see that in the array, by the way? Excuse me. Do you see 1041? Nope. What's wrong? This very non-idiomatic for loop here. I'm going too far. All right? Fine. Let's fix it. Quit. What should it be? Less than. Strictly less than. Okay. Great. Iterative development here. A.out, 10 things. Right. Oh, that looks a lot better. Okay. Except that, are you always going to expect an integer value for averages of integers? Excuse me. That seems highly suspect. So let's go ahead and go GDB A.out. Set my args again. Layout source. And then break average. And run. I don't want to have to go through that loop again because I know I've fixed it. So let me go ahead and set a breakpoint at line 59 and continue with the operations. Now let's print sum. Print the array. 6, 7, 8, 17, 29, 34, and 42. Right? I count 42, do you? So it seems like the sum is correct. Print n. 10. It should be 4.2, right? Next. Next. Now let's print the average, what was returned from that function. 4.2? Nope. What was wrong? Excuse me. Integer truncation. Solution? Put in a double. I think that was the last bug that I put in there. Oops. And now when this runs, it should be correct. All right? Correct, 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 correct. Of course, pull out your calculator and make sure. Okay? So to review, what were some of the commands that we ended up running? Well, to run it, you use GDB a.out. Once you're in there, you hit run. You can go layout next, or if you just want to look at your source code, layout src. Sometimes it screws up and you need to refresh it, so just type out refresh. You can break at a particular function by naming that function, or you can break at a particular line number, 12. If you've got multiple files, you can specify a source file, followed by a colon, and then the line number that you want to break at. You can clear your breakpoints by clearing out the original name of the breakpoint, or clearing out by line number. So if you set whatever, then you can clear whatever. Right? You can resume the program with continue. You can use print and a variable name to print the variable name, or you can watch it. You can watch that variable, and then any change to that variable will be automatically reported and printed out to you. If you get caught in an infinite loop, you can halt the program by doing Control-C, and then it'll stop. And then you can take a look around and resume or whatever, continue or go step by step. You can, again, refresh. Setting arguments, set args, and then just like you would regular arguments. You can also have conditional breakpoints. Break at line 10 if x is equal to 21. Any C code conditional you can put in there. Right? So you can put it in and or whatever you want. Okay? Questions on that? Otherwise, with the remainder of our... And do we need to retread the debugger in CS50 or not? Do you want to see that again? Yes? Okay. I need something to play with then. CD main. Oh, okay. I need to refresh apparently. I lost my connection. Let's see, bounds. There we go. I'm just going to steal this program right here. And then open demo. Right. There we go. So GCC demo with a G, demo.c. Right. Now this bug, the CS50 IDE debugger is a little bit more graphical. But it is not as powerful in my opinion. You can't set, at least I don't know how to set conditional breakpoints or do certain things with it. But once you've compiled in exactly the same way, you can go with debug 50 a.out, and that'll launch, you have to set a breakpoint graphically here. Let's just go ahead and set a breakpoint right here. Right? So you can set a breakpoint by clicking to the left of a line number. You can unset it by clicking it again. You can set as many breakpoints as you want. I'm only going to set one here. And then you can run it. It pops out over here. You can see the breakpoints. Excuse me. argc, there's only one argument. argv, well, there's no way to print it. Okay, no, you can expand it out, I think. There we go. And it's a.out. You can see right here, it's very small up on the screen, but you can see it on your own computer. Array is uninitialized. N is uninitialized, so if we go next, and I think we could do that by going next here. This is basically step. So next, next, and then you can see N right here is changed to 100. Next, 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 next. This is an array, so there's no convenient way of printing an array or finding out what it is. Oh, that's unfortunate. So that's one of the drawbacks, I guess. There might be a way of doing it. I'm not too familiar with this, but print? Nope. There's nothing I can do over here. Intermediate? I don't know. So unfortunately, it doesn't look like there's a way to look at the contents of that array to make sure that they're correct. Continue. Step into. Step out of. Deactivate all breakpoints. And then this play button, I'm sure, is a resume. So if we wanted to resume down here at line 15, because I don't want to go over that 100 iteration loop, you can go ahead and continue, and it'll jump all the way down there. Right. And then you can start walking again, or what would start going next, next, next. 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 Nope. Okay, it already died. Or something. I'm not sure. Play? Nope. So, it died. Stop, clear all those, and then I guess I'm just gonna have to kill it. Oh no, it doesn't even let me kill it. Okay, great. If I close you, I can still close it. Fine. I don't know what's gonna happen if I continue doing other things though. Oh, it's not even going to let me open it up another terminal. Oh, I hope I didn't donk the entire thing. Nope, we're good. Oh, no, the break, it's still going though. Play. There we go. Now it's done. Okay. So again, GDB is way more powerful in my opinion. There's a whole bunch of other commands that you can do. But if you want the graphical version of it, then debug 50 is what you can use in the CS50 IDE here. Okay. So I'll give you a choice. Since we only have about a half hour left, here's last year's midterm. Same format last year as it is this year. You'll have 24 hours. It'll open up on Canvas the midnight of the 20th. You'll have the midnight morning of the 20th, and then you'll have 24 hours to do it whenever you want. Right? You submit it, resubmit it. There will be a grader available for it, and it'll spit out results just like your hacks and your labs and stuff like that. We will be available to answer questions. No collaboration with anybody else. You can ask questions, but you are allowed to ask questions, of course. But we might not give you the same level of answers as we would on a hack. Right? So this is last year's. First of all, there's a FizzBuzz. You did that in that was Give Me Points last year. You did that in your Lab 3, I believe, or Lab 4. There's a program to compute the body surface area estimate of a human, given their weight and height, using several different formulas. There's a Du Bois formula, a Haycock, Boyd, and then an average of those three formulas. And here are the formulas to do that. Or there's a series of array exercises. The dot product, the bias dot product, or a filter method where you're given an array, and then you have to pull out all the positive numbers and return a new array containing only the positives. So I'll give you the choice, and that was it, by the way. What do we want to do? FizzBuzz? Oh, really? Oh, okay. No, that's the simplest one. Yeah. 24 hours. That entire 24 hours. I mean, it's designed only for 1 hour, 15 minutes, if you know what you're doing. But if you want to take 2 hours, if it takes you 2 hours, 3 hours, that's up to you. If you want to do the first one, go to lunch, come back. It's completely asynchronous. Open book, open note, open computer, obviously, because you're not going to be here. But closed collaboration. Do not collaborate with anybody else. Remember that tool that we use, MOS, Measure of Software Similarity. You will be caught if you're copying off somebody or if you're closely collaborating with them enough that your code looks almost the same. It's really, really easy to catch. Yeah. The 20th, so 1 week from today, that morning, midnight that morning. So 12:01 a.m. October 20th. It closes at 11:59 p.m. October 20th. There, I shaved. You don't have 24 hours now. You have 24 hours minus 2 minutes to make it absolutely clear. Okay. BSA, not Boy Scouts of America, but body surface area, or array exercises. Array exercises, okay. Increase the size here a little bit, zoom in. So this is the first one that we're going to write, a dot product. A dot product is simply you take two arrays, and in fact there's an example here. Here's the first array, here's the second array. You take the first two elements, you multiply them together. You take the second two elements and you multiply them together. Third elements, multiply them together, and then you add them all up. Right? 24 here. So -2 is the first element, 9 is the first element in the second array. So -2 times 9 plus 5 times 4 plus 3 times 8, etc., etc. So we're given this this function that we have to the signature of this function that we have to use. Array utils and array utils.c. There we go. So I put my prototype in the header file, and you will be graded on all the usual stuff that you grade. We grade for hacks. So to do documentation, and one of the most common things that we're not seeing is to do author header. Right? That's free points by now, right? And if you don't put your name on it, then you lose a point on your hack. Right? Okay. Let's go ahead and go over here to the source file. Right, there we go. Now remember that there is a return value here that is an error code. So where are we putting the result? We're putting it in this pass by reference variable, int star. So it should return an error code for any and all error conditions. The result of the dot product is the computation should be put into the last argument here, result. All right. So help me out. Where do I start? What's the first thing you do in a function? Check for null, check for other error conditions. So if A could be null, what else could be null? Or B is null. What else could be null? Anything? Could N be null? No, N is just a pass by value variable. It'll never be null because it's not a pointer. But what else could be null? Result. Right. So I've taken care of A, B, and the result. What is an invalid value for N? Okay, I'll buy that. If it's a negatively sized array, then I will return just an error code here. If you want to go to the trouble of making an enumerated type for your error codes, great. Go ahead and do that. Right. Otherwise, if there's no error, what should I return? 0 for no error. Right? All right, error handling is taken care of. Now I actually need to compute the result. So what kind of a loop do you want to write? A while loop? For loop? For loop. An idiomatic for loop. For int I equals 0, I is less than n, I plus plus. Right? Now what am I going to do? I'm going to be summing things up, right? So int sum. Yeah, good. Don't make the same mistake that we just corrected in GDB. Sum is equal to, where should I start it out as? 0. Sum plus equals array, or A sub I, times B sub I. We're not taking an average or anything like that. We're just summing up all the components of the two arrays. Okay. Done? Nope. But suppose I am done. Suppose I think I'm done. I've got a tester file over here. How do I know that it's correct or not if I don't at least test it on one thing? This is ad hoc testing. That's the bare minimum of what you need to do. Right? We gave you a starter tester file for, say, your arrays. We also gave you an image driver that allowed you to actually see the images being flipped upside down, left, right, whatever it was. Right? So let's go ahead and compute this dot product here. Error code is equal to, what was it called again? Dot product of ARR, BRR, and its size, and then finally a result. Uh-oh, so what does that mean? I need a integer variable to hold that result. There we go. Is that how I call a function? A pass by reference function? This is a pointer. Result is not a pointer. How do I make it into a pointer? In fact, if I tried to compile this right now, GCC C array util, oops, where am I? I'm not in the midterm. GCC C array utils dot C. Right. Oh, great. It's also telling me what? What didn't I do in here? I didn't do several things in the source file. I need to include the standard library, stdlib. I'm not using any math stuff yet, other than multiplication, and that's not part of the math library. But what else am I using? I need to include array utils.h. That should take care of most of the stuff. All right, there. GCC array utils.o and array demo. I can also turn on all of the warnings here. What's going on? Result is an uninitialized in this function. Right? Okay, fine, it's uninitialized, but also, where's the actual warning? Implicit declaration of dot product. Come on. Okay, so I need to get the correct warning here. There. Now that should work to get the correct warning. It's uninitialized. You didn't use the error code. And here's what I was looking for. It's expecting an integer pointer, but I give it a regular old integer. So how do I take a regular old integer and turn it into a pointer? Ampersand. And then I can print out the results. Printf error code is equal to %d and the line. Make sure that your error is working as well. Error code. Right? And then I need to print out the dot product. Printf dot product is %d and the line result. How do I know what the correct value is? Dot product is 0. -2 times 9. What was it again? It's in the, this one was given to you in the handout. 24 it should be. If I didn't have this 24, what would I have done? Pull out your calculator and compute it. Right? That's how you need a secondary means to determine what the correct output should look like. Right? Okay. So what was the problem? I never actually did anything with the sum. All right, I need to put the sum into the result. Is that how we do it? Sum is a regular old integer. Result is a pointer. So how do I take a pointer and make it into a regular old integer so I can put the sum into it? Dereference it. Right. So I need to recompile everything from the beginning. And now, fingers crossed, it should be 24 again. 24. Right? That's a reasonable amount of testing. Actually, that's the bare minimum of testing to make sure that it at least works on one thing. Right? Then you can throw it in the grader and see if it works. But you really should be doing more test cases. Okay. Next one. I can get rid of this now. Let's see. Biased dot product. Write a function similar to the first that takes two arrays of integers of both of size n and computes their biased dot product. With the biased dot product, the products are only added if they are positive. Right? So, for example, -2 times 9, that would be negative. We don't add that. 5 times 4, that is positive, so we end up adding it. 3 times 8, that's positive, so we end up adding it. Right? 2 times 0, that's 0. Is that positive? Nope. It wouldn't matter if we added it by the way anyway, because it'd still be 0. And then 1 times -2, that would end up being negative, so we don't add that. Right? So this should end up being 44. Okay? Only if they're a positive. Okay? So dot product, biased dot product. Okay? Exact same error checking as before. Exact same almost for loop as before. Right? But how do I change it? Let's go ahead and put it into a temporary variable first of all. Int temp is equal to this. Now, if the temporary variable is positive, then we add it. Sum plus equals temp. Right? No? I think that's okay, right? All right. We, of course, need to put this into our header file and make sure that you've got documentation. There we go. And let's go ahead and make sure that it works on at least one test case. I'm just going to go ahead and simply change this. Probably wouldn't want to do that, though, because you'd want to make sure that everything works all together. So you'd write some more code. Right? So the bias.product is, and it should be, what was it, 44? Oh, great. One more, although we did do this in class, I think, at one point. Filter positive. Write a function that takes an array of integers of size n and returns a new array of integers containing only positive values from ARR. The size of the new array should be communicated using this pass by reference variable over here, right? Because if we use, say, A here, if we use this, would I know that you would not include 2, you would only include 5, 3, 2, and 1. Right? So how do you know that the new array that you're giving me is of size 4? I have to be told that. If I knew that, then I'm doing half your work for you. Right? I'm going through and counting up at least the number of positives. Okay? All right. So let's bring this over here and put the prototype in the header file. And let's actually go ahead and implement this. Help me out. What's the first thing I should do? Say what? Should I call malloc immediately? No. What's the first thing I should do? Do some error handling. The most common mistake we saw with hack 7 was that some people did error handling on one function, but then ignored all of the other functions, right? If you're doing error handling, do them on all, right? So if ARR is null, or if new size is null, or if n is less than 0, then that's an error. And don't forget to return 0 for no error. Otherwise, some random value may be returned. Okay? All right, that's good. By the way, can I make changes to the original array here? Nope. Any attempt to do so will be a compiler error because of const. Okay? So, what's the next step? Second step. I need to know how many positives there are in order to create a new array, right? So, int num positives equals 0. Always initialize your variables. Then an idiomatic for loop. For I equals 0, I is less than n, I plus plus. For each element in the array, if the ith element is positive, not if it's equal to 0, I'm not including zeros, only positive numbers. If it's positive, then increment my counter. There we go. Once I know how many things it should be in the resulting array, now I can allocate memory. Is this correct? Result of num positives. Nope. What am I doing there? That's a static array. Where is this static array allocated? on the stack, in the stack frame. When we return from this function, that stack frame is popped off the top and is gone and destroyed. So I need to use a dynamic array. Result is equal to a call to malloc, typecasting the returned void pointer. Malloc, how many do I want? Num positives, times size of, is it int star? That's for two-dimensional arrays. I don't want an array of pointers. I want an array of integers. Size of int. There we go. Am I going to end up returning result? Nope. Sorry. Oh, yeah, I am. Yeah, I do. So return result. Ooh, okay. Oh, I'm glad I did this. I lost the forest for the trees. Let's go back and revisit this error handling now. Okay, so what could I return? Again, it has to be an integer pointer. In fact, what does the handout say? Size of your new arrays, blah, blah, blah. I think it's down here somewhere. You should just do reasonable error handling. All right, so if any of these things occur, can I return 1, like I did before? 1 as a memory address may or may not exist. It probably doesn't belong to me. Can I return 0? Nope, that's almost equivalent to null. So I should do null. Just like malloc. If malloc fails, the only way that it can tell you that it failed is by saying, I was not able to allocate the memory here. Here's your pointer is null. All right. Done. What's in that array right now? Nothing, garbage, dead beef, who knows? I never copied over all the positive numbers. So once again, let's go through our idiomatic for loop here. If the number is positive, I should put it into the array. Results of I is equal to arrays of I. Now let's think about that. Right? That's a 1-for-1 copy. The first one will get copied if it's positive. The second one will get copied if it's positive. This one was not positive. This one was negative. So we didn't end up copying anything there. And so we went on, copied, copied, copied. Right? We have a gap. Right? Can I use the same I for result as I do for array over here? Nope. I need yet another variable. We'll go ahead and go with j here, initializing it to 0. And then we'll use j on the result. You can call it k, you can swap I and j if you want to, I don't care. Right? But then what else do we need to do? Once we put something into the result, yes, this is positive, put it in there. Yes, this is positive, put it in there. No, this is not positive, don't put it in there. Right? So don't advance your j index over here. But if you do copy things over, you need to advance so that you're copying the first one, then the second one, then skipping the third one, you don't advance it, going to the fourth one, fifth one, whatever. Okay? Now are we done? One last thing. Did I do anything with new size? In fact, other than checking that it's null? So, new size is equal to the number of positives. Is that correct, though? It's a pass by reference variable, so what do I need to do to it? Dereference it to make it into a regular old variable so I can put a result into it. Right. Let's see if this compiles. Great, it works. And the last thing that we'll do is test it really quick here. Let's do it on BRR. So int CRR cur is equal to, what is it called? Filter positive of BRR, and then the original size is n, the new size will be that result. Right? Then for int I equals 0, I is less than result, I plus plus, printf cur sub %d is equal to %d, and the line, and I, and CRR of I. Not cur, but cur. Right? So what should we expect? Before I run this, what should we expect? 9, 4, and 8 are all positive. 0 is not positive, negative 2 is not positive. So I should expect it to be 9, 4, and 8. Right, crossing my fingers here, 9, 4, 8. Excellent. We definitely don't have time to do BSA, the first one here. But just to run through how you would do this, there's just 3 formulas. You read stuff in from the command line as command line arguments. I believe that you read in the weight in kilograms of a patient, their height in centimeters. You put them into these formulas here. How are you going to get the square root? Math library, right? SQRT. How are you going to raise a number to the power of 0.3964? What function allows you to do that? Pow. What function allows you to get the natural logarithm of a number? Log, right? Natural log base E. Right? Once you just plug and chug these into these formulas here, you report them to the standard output. In fact, they're 6 decimals of accuracy here. How would you take the average of all these? Add them all up and divide by 3. So pretty straightforward for this one. The only thing is reading those in is command line arguments. Argv of 0, argv of 2. How do you convert an argument into a double? A to F. Right? Any questions? No? All right, then. Good luck if you have any other midterms or whatever. But otherwise, I'll see you a couple weeks from now, I guess. I'll see you virtually next week, though.